Example number 2. Traffic flow is defined as the rate at which cars pass through an intersection, measured in cars per minute. The traffic flow at a particular intersection is modeled by the function f, defined as you see there, where f of t is measured in cars per minute and t is measured in minutes. Alright, before we answer a bunch of questions, we always want to kind of digest this and see what is the stuff that we're talking about. And I don't see stuff defined anywhere, so I get to choose a variable, and I'm going to choose q of t to be my stuff. In this case, oh geez, what is the stuff? The number of cars that passed through the intersection? Now, what is the f of t then? If q of t is the amount of cars that passed through the intersection at time t, then f of t, the traffic flow, is going to be our rate in, rate through, or rate in, our traffic flow. And then what is the rate out? There is no rate out. A student this year described it best when he said, once you pass through an intersection, you can't unpass through the intersection. Suppose my wife leaves to go to work and she passes through a said intersection. Forgot something, turns around, comes back through the intersection, grabs the thing she needs, and then goes off to work, passing through the intersection a third time. Engineers doing the study would count her as passing through the intersection 3 times. Wouldn't say, well, she came back, so that went through the intersection. So there's only a rate in. Once you enter the intersection, there's no undoing it. Part A. To the nearest whole number, how many cars pass through the intersection over the 30-minute period? Well, we're going to integrate the infinite sum from 0 to 30 of our rate f of t dt. Again, rate times time. And we're summing up all these rate times times, and that's going to give us 2,474 cars. What I have done is entered my f of t function into the y1 as f of x. Please make sure you're in radians. Perhaps your answer is close, but not exactly the same as mine. There's a good chance you might be in degrees. Now let's take a look at example part B. What is the average traffic flow over the time 10 to 15? There are 2 types of averages that we've talked about in this unit. One is average value and one is average rate of change. Traffic flow is a rate of change, but when they ask for the average traffic flow, they're not asking for a rate of change. They're asking for the average. The question didn't ask for this, but it could very well have said average value of the traffic flow. So if it asks what is the average value of traffic flow, that should prompt integral over interval. Whereas in part C, it says what is the average rate of change of the traffic flow, telling us the change in y over the change in x, so to speak. Anyway, example B. What is the average value of traffic flow? Or f of t. So the average value of f of t is the integral 10 to 15 f of t dt divided by the interval 15 minus 10, often written 1 over 5 times 10 to 15 f of t dt. That answer will come out to be 81.899, and the unit is going to be cars per minute. The integral over this rate would give us the number of cars, and then the interval as units of time, minutes. So cars over minutes. Cars per minute. Part C wants the average rate change of traffic flow. So that's going to be our difference quotient. F of 15 minus f of 10 all over 15 minus 10. That answer will come out to be 1.518, and the unit will be cars per minute squared. The numerator, which represents traffic flow, is in cars per minute, and then we're dividing by minutes, so it's cars per minute, or cars per minute squared. Looks like we didn't need the Q of t after all. The only thing we could have said was Q prime of t, the rate at which the amount of cars passing through the intersection at time t, is actually our f of t. It is our rate in, with no rate out. That is the end of example 2. Example number 3. This was the real AP question in 2010. It was the third question, a calculator question. Alright, let's digest this. There are 700 people in line for a popular amusement park ride when the ride begins operating in the morning. Once it begins operation, the ride accepts passengers until the park closes 8 hours later. While there is a line, people move onto the ride at a rate of 800 people per hour. The graph above shows the rate r of t at which people arrive at the ride throughout the day. Time t is measured in hours from the time the ride begins operation. One of the reasons that this problem is a little tricky, it's hard to digest what is the quantity. The thing that we are actually addressing here, which I will call Q of t, is actually the number of people on the ride's line. The key to that being the number of people on the line is the key part. The line. So the rate in would be the number of people entering the line. Arriving to the ride means entering the line. So rate in is represented by this function r of t. That's the graph, is the rate in. The rate out is simply the function 800. So people will leave the line to get on the ride. They will leave the line at a rate of 800 people per hour. That's the rate out of the line. That's constant. Part A, how many people arrived at the line, or at the ride's line? How many people arrive between t equals 0 and t equals 3? Show the computations that led to your answer. So what we want to find is the integral from 0 to 3 of r of t dt. That would be integrating rate times time of coming into the line. In effort to find this, we're going to come over to our graph, and we have to appeal to geometry to find this integral. If you see here, I'm looking at this as two different trapezoids. The first trapezoid being here, and the second trapezoid being here. We talked about this in an earlier video, where the trapezoid is average of the bases times the height. So let's work out each one of these parts. For the red trapezoid, the first base is 1,000. The second base is 1,200. We're going to average those bases, so divide by 2, and then multiply that by its height of 2. See, I'm appealing to geometry. And then I'm going to add to that the pinkish trapezoid, which has bases of 1,200 and 800. Divide that by 2, but the respective height of that is 1. See, this is a height of 1, while this was a height of 2. This is a calculator question, but I don't think you need it for part A, because the first part is going to give me 2200, and then the second trapezoid is going to give me 1000, so that's going to give me 3200, and that's 3200 people. That's 3,200 people entered the ride's line between the hours of 0 and 3. Part B. I'm going to go over here and draw the graph for the rate of people leaving the line. Because in Part B, it wants to know, is the number of people waiting in the line to get on the ride increasing or decreasing between t equals 2 and t equals 3. First, let's just analyze what is happening at exactly time 2. At time 2, people are entering the line at a rate of 1,200 people per hour. But at that very same time, people are leaving the line at a rate of 800 people per hour. So there are more people entering the line than leaving the line, so the line is going to increase in size. So over here, I'm going to say that on the interval 2 to 3, our rate in is greater than our rate out, and therefore the number of people in the line is increasing between t equals 2 and t equals 3 hours. Part C. At what time t is the line for the ride the longest, and then how many people are in line at that time? Well, I can see something very special happens here at time 3. That's when the rate into the line is equal to the rate out of the line, so you could say the line is not changing at all. The line is at rest when t equals 3. But before 3, the rate at which people entered the line was greater than the people leaving the line. Then after time 3, the rate at which people entered the line was less than the rate of people getting off, which would indicate that the line is shrinking. I like to say that Q prime of t, which is our R of t minus 800, equals 0 at t equals 3. See, I like to say Q prime of t. You wouldn't necessarily need that. You could simply say R of t minus 800 equals 0 at time t equals 3. It's important to identify that critical t value. Now on the time interval, 0 to 3, our R of t is greater than 800, meaning Q prime of t is greater than 0. While on the interval 3 to 8, R of t is less than 800, meaning Q prime of t is less than 0. So Q prime will equal 0 at t equals 3. The derivative will change from positive to negative, and this will make not just a local maximum of the line, but an absolute max, because it is increasing the derivative is increasing the whole way from 0 to 3 and then decreasing the whole way from 3 to 8. I will say that the line is max at t equals 3. We are also asked to find how many people are actually in the line then when it is max. So how many people are in the line at time 3? Please remember to consider how many people were in the line when we first started. Q at 0. Then we're going to add to this the integral from 0 to 3 of R of t dt, and then we are going to subtract from this the integral from 0 to 3 of 800 dt. This is the amount of people coming onto the line. This is the amount of people leaving or that had left the line, and this is the starting number of people. So we have to read the problem to see that there were 700 people initially, and then I have to take the integral from 0 to 3 of r of t dt. That will be done on my calculator. I don't necessarily need a calculator here. This is going to be 800 times 3. And then this will give us 1,500 people are on the line at time 3. Finally, part D, write but do not solve an equation involving an integral expression of r whose solution gives the earliest time at which there is no longer a line for the ride. So we want to find when q of t equals 0. Q of t function will be 700 plus the integral from 0 to t, r of, I need a dummy variable, let's call it again u, minus 800 times t. And we want to see when that will equal 0.